quick review of yesterday. The force of friction is dependent on the coefficient of friction and the normal force. So the harder the two surfaces are pushed together, that's normal force, the more friction there will be. The stickier the two surfaces are, mu, the more friction there will be. All right? So we started looking at that in terms of inclined planes, that we have to find that second side, okay, the normal force in that internal triangle if we're given coefficient of friction, right? So that's what this question here is about, so I'd like you to copy that one down and give it a try here to start out with, and we'll use it to kind of review. And guys, if you haven't submitted your Newton lab, make sure you do that in the next like 10 seconds, 15 seconds, okay, if you haven't already, right? And I won't mark it late, right? Even though it'll tell you it's late. Just tells you that because I make it 10, 11 when class actually starts. Okay, but if you get it in the next 15 seconds, I won't mark it late. Okay. So we have our inclined plane, okay, that's angled at 40 degrees. Okay, so we got our 40-degree angle here, and we have our 20-kilogram box on there, okay? The coefficient of friction is 0.185, okay? And we want to find the acceleration. So, obviously then, we have F parallel acting down the ramp. We have the force of friction acting up the ramp, okay? And we're going to need to calculate those things. So in order to do that, we have to calculate all three sides of our inclined plane triangle. So we'll need Fg, which will be 196.2 newtons. Okay, we'll need normal force, which we calculate by going the cos of 20 degrees, okay, times 196.2. Cos of 40 degrees, sorry. Okay, so cos of 20 degrees, no, see, and I said it's 40. Cos of 40 degrees times 196.2. All right, so that side's 150.30. And then we also need F parallel. That'll be the sine of 40, not 20. Okay, sine of 40 times 196.2. All right, so that's 126.11. Okay, now that I have normal force, now I can use this formula to get the force of friction that's going up the ramp. Okay, so we'll have our normal force times 0.185. There's our force of friction, 27.8. Okay, and now we can get our net force by going sum of all forces, so our 126.11 minus our 27.8. So that one minus that one. There's my net force, 98 newtons, and if I divide that by my mass, I've got my acceleration. So my acceleration there is going to be 4.9 meters per second squared down the ramp. Okay, everybody all right with that one? Okay, so expect you would easily see one like that on a quiz, possibly tomorrow. Okay, or something like that. All right, now I'm going to give you one that's a bit more of a thinker. It's not an inclined plane. This is being pulled at an angle along. Oh, sorry, no, that one's not being. It's being pulled horizontally. That's not the one. Where's the one with the angle? This one. Okay, we'll do that one in a minute. I want you guys to try this one first. Okay, then we'll get into the angled one. Okay, so on this one here, okay, we have the 20-kilogram box being pulled horizontally by a force of 200 newtons. Okay, so we know we've got this. Okay, 200 newtons. We know the coefficient of friction is 0.8, so this is high friction. Okay, that's a very high coefficient of friction. We're looking for the acceleration of the box. All right, if I want to calculate the force of friction, which I'm going to need because it's in opposition to the 200, I'm going to need to use that formula we learned. Mu times the normal force. Okay, so I've got to find the normal force. Normal force is going to be equal to what force in this situation? Right, force of gravity. It's a level surface. The applied force is straight horizontal, so the box isn't being lifted or pulled down into the table in any way. Okay, so these two forces will be equal. Right, so 196.2 and 196.2. Right, now that I have that, I can go 0.8 times 196.2, okay, and I'll have my force of friction. 196.2 times 0.8, okay, gives me 156, and then I go 200 minus that answer. There's my net force, 43.04, okay, divide that by the mass, and I've got my acceleration, 2.15 meters per second. Actually, sorry, there's only 2 sig digs, 2.2 meters per second squared forwards, or along the table, something like that. Okay, now, I made kind of a point here of saying that 200 newtons is straight horizontal, because it makes a difference. If you pull at an angle, you change the amount of friction. So if I didn't pull this straight horizontally, like we have here, but instead pulled like this, that doesn't mean the box is going to go that way. The box is still going to slide horizontally along the table, provided I don't pull too hard. Okay? If I pull at that angle really hard, yes, it will fly off the table. Okay? But if I pull it just the right amount, it still slides along the table. But I reduce the amount of friction. And I showed you that yesterday with the desk. How is it that I reduce the amount of friction by pulling at an angle? I don't reduce the force of gravity, but I reduce the normal force, right? Okay. What I'm doing is holding some of the force of gravity in this tension. Okay. I'm holding some of the box's weight off of the table, which means the table doesn't have to push as hard, and now there's going to be less normal force and thus less friction. Okay. Now, how do I figure out what my normal force will be in this situation if, let's say, now this is let's say 400 newtons, and this angle is 20 degrees. How do I find what my normal force will be now? Now that I know some of that 196.2 is no longer sitting on the table.
Probably some trade.
Yep, exactly, some trade. Okay. If I'm pulling at an angle, I'm pulling horizontally as well as vertically. Whatever that vertical component is, okay? So if I'm looking at this thing here, this would be the horizontal component. So we'll call that F horizontal, okay? And then this would be the vertical component of that. That's the part of my pulling that is holding the weight off the table. Okay? So if I figure out what that is, then I just put it on here. I change my free body diagram to reflect that now, yes, I've still got normal force here, but it's not equal to gravity anymore. Okay? I've got this additional force acting up. Now, since the box is still not moving vertically, Fv and Fn still add up to what number? Right, the same as gravity, right? If the box isn't going to move vertically, my net force is still 0. And that's what she meant. Okay? She meant net force was 0. Okay? So these two things add up to 196.2, and they completely offset gravity. That's important because I can calculate what Fv is. That will allow me to calculate what F normal is now that I'm bearing some of the weight. I would go 196.2 minus Fv, whatever's left, is the amount of weight still sitting on the table, and thus the normal force. And then I can use that here to calculate my force of friction. Okay, so it's a couple of extra steps, but it's something a lot of people miss when they look at a question like that. They forget that pulling at an angle means you're also pulling upwards. They get the whole horizontal part, they figure that out, no problem. But they forget the role that that vertical component plays in reducing the force of friction.
Does surface area play any effect on friction?
Okay, question that always comes up, good question. Does surface area play a role in the force of friction? Yes and no. In terms of, and because usually the reason people ask this is they look at like tires, right? And you see that, you know, like high performance cars have really wide tires, okay? And that's, in everybody's mind, that's to increase traction. It does, to an extent, increase traction, but it doesn't affect this.
So does it affect the mu?
It affects mu, and here's how it affects mu. If you spin your tires, especially if it's not icy, if it's just on like bare asphalt, what happens to the tire? It smokes. It essentially vulcanizes. That means it burns. Okay? It liquefies and burns. Okay? Well, that's because it gets hot. So the increased surface area gives a greater area over which heat can dissipate. And so that can keep the rubber intact longer, which helps to maintain mu. If the tire starts to vulcanize and smoke, its mu goes way down. Okay? And it's not nearly as sticky, and it doesn't work as well. Okay? So that's kind of the role that surface area plays. It's about the dissipation of heat and maintaining mu. It has nothing to do with like normal force. People are like, oh, I spread the weight over a bigger area. Well, it's still the weight. It doesn't matter whether that's spread out or not. It's still normal force is normal force. Where it helps is in the coefficient of friction. Okay, so now that we've looked at that, I want you to try this one. Look, it's the same number, 400 newtons. Okay. All right, 10-degree angle, 400 newtons worth of tension in the angled string or whatever we're pulling the 20-kilogram box with, and the coefficient of friction is 0.255. I want you to calculate the acceleration of the box. It is still moving along the table. Okay, so on a question like this, because we know the box is moving horizontally, we want to try and remove the angled force. And we remove the angled force by finding its components, vertical and horizontal. Okay, so we're going to find what the horizontal component is. Okay, here. Okay, we'll call that force horizontal, and that's simply going to be the cos of 10 times 400. All right, so 393.92 newtons. All right, and finding its vertical component. All right, which we'll do by finding the sine of 10 times 400. All right, so that side is 69.46 newtons. Okay, now that I've got that, now I can effectively do this. I've broken that force up into the two things it effectively produces. A vertical force of 69.46 newtons and a horizontal force of 393.92 newtons. Everybody with me there? All right, so now what I do is I just reorient these. Okay, I put them there, and I take this one, and I put it here. All right. Now, the other force I've got to put there is normal force. It's going to be quite a bit bigger, but I don't have room to draw it bigger. The box is moving along the table, so the net force vertically is what? Is 0. Okay, so I know that my force of gravity down here of 196.2 newtons is what normal force and the force vertical add up to. So if I want to find my normal force, all I have to do is take the 196.2 and subtract the 69.46. Because whatever's left is how big normal force is, or the remainder of the weight still sitting on the table. All right, so I'll take my 196.2 and I'm going to subtract my previous answer there. All right, so my normal force is 126.7 newtons. Okay, now that I know that, now I can finally find the force of friction that is opposing the horizontal component going forward. Okay, I had to do all this work just to get this force over here. Okay, now that I've got all this vertical stuff, I actually don't need to do anything with it after this. Okay, the box isn't moving vertically. I just needed to use that to my advantage so that I could find Fn. Right, now that I have Fn, now I can find force of friction. 0.255 mu times normal force, 126.7. Okay, that'll help me to get the force of friction. So, times 0.255. All right, so my force of friction is 32.3 newtons. Okay, so now that I've got that, now I can calculate my net force. Okay, these all add up to 0, so I'm not going to use those at all. I'm just going to take the 393.92 and I'm going to subtract the force of friction. Okay, there's my net force, 361.6 newtons forward, and then to find the acceleration, I just divide that by the mass, 20. Okay, so my acceleration is big. Okay, somebody like grabbed this and like jerked it really hard. Okay, and it's accelerating at 18 meters per second squared to the right. All right, everybody okay with that?
So don't give us directions, you just like say along the table or plus 18 meters.
Yeah, I would say along the table is probably, like in the question they would say to the right or forward or something like that. Yeah, they would give you a vector that you could work with. Okay, everybody good with how that one worked? Okay, that's about as tricky as a friction question gets. Okay. That said, there's never been a unit exam where I didn't have this question. Whoops, that was out loud. Okay. All right, so that's it for the friction stuff. Okay, what I want to do today is finish up those worksheets now that we can finally do all the ones that involve coefficient of friction. And then tomorrow, I'm going to look and see if we can get the computers. If we can, we're going to do the lab on friction tomorrow. Okay? If not, then we'll do it when we come back on Monday.